Good day, students. Welcome to part one of definite integrals using limits of Riemann sums and confirming your answers using the tools of geometry. The instructions for the examples are as follows. We are to express the following limit of Riemann sums as a definite integral. We're to evaluate the integral algebraically using the rules of integration. And then we're to confirm our results using the geometry of the function. Okay. So before we start, let's look at the formula that relates the limit of the Riemann sum to the definite integral. Okay, so let's write this down formula. So let's start with the limit of the Riemann sum. Okay, so let's say we have a function that's integrable, okay, on the interval AB. So the limit as the norm of the partition approaches 0 of the discrete sum from k equals 1 to n of the function c sub k will be our independent variable here, delta x sub k. This limit right here, limit of a Riemann sum on an interval AB is equal to, in condensed form, the definite integral from the lower limit of the interval, which is a, all the way to b, of f of x dx. Okay? So this is a nice condensed version of representing Riemann's sum, the limit of Riemann's sum. All right? All right, let's take a look at the first example. Question number 1. We have a limit of Riemann's sum given by the limit as the norm of the partition approaches 0 of the discrete sum from k equals 1 to n of c sub k plus 1 delta x sub k on the interval 1 to 5. Okay? All right, now how do we express this as a definite integral? Well, this is how you go about doing it. If you look at the formula we have right here, this delta x sub k basically changes into dx, as you can see here. The interval is basically your limit of integration. Okay, this is where you start, this is where you end. And then c sub k changes into x. And then everything else drops off. All right, so let's go ahead and apply that idea here. C sub k is going to become, well, let's write out our limit of integration first. So we're going to be integrating from 1 to 5, as you can see here, 1 to 5. Now this function just involves replacing c sub k with x. So it's going to be x plus 1, and delta x sub k will be written as dx. Okay, so this is the definite integral notation of this Riemann limit of Riemann sum right here. Okay, now we have the integral, the definite integral. Now let's evaluate it using algebra. Okay, so let's see. Part A was to integrate, express it as a definite integral. Part B, algebraic determination of the definite integral. So let's call this algebraic approach. Algebraic approach. Now to find the definite integral algebraically, we're just simply going to use the formulas for integration. Okay, we're going to be using the power rule here. Let's review that real quick. Power for integrals, if you're integrating x to the n dx, it's simply x to the n plus 1 over n plus 1, okay? Plus c, of course, if it's an indefinite integral. But this one is definite, so we don't need the c component, all right? So let's go ahead and do that here. So if we wanted to find the integral from 1 to 5 of x plus 1 dx, we're going to apply the power rule twice to the x and then the 1, okay? You can look at this one as having x to the 0th power. So this is going to become x to the, there was a 1 here before, so using this formula is going to be 1 plus 1 over whatever that power is, 1 plus 1 also, okay? And then plus, this one will simply have x to the 0 plus 1 over 0 plus 1. And that will be evaluated from 1 to 5. All right? So if we simplify this a little bit, we'll have the antiderivative of x plus 1 as x squared over 2 plus x. All right? So that's basically that. And we're going to be evaluating it from 1 to 5. So we are going to evaluate the antiderivative at 5 minus the antiderivative at 1. Okay, so you plug in the upper limit of integration. You're going to have 5 squared over 2 plus 5 minus what you get when you plug in the lower limit of integration into your antiderivative, which is 1 squared over 2 plus 1. All right? If I simplify this part right here, we'll have 25 over 2 plus, let's express 5 as a fraction with 2 as its denominator. So if we do that, 5 over 1 can be expressed as 10 over 2 minus, simplify this, 1 over 2. And then if you distribute this minus to this plus, minus, if I express 1 as a fraction of 2, this will be 2 over 2. All right? And then if we simplify that, we're going to have 25 plus 10, which is 35, minus 3, which is 32. 32 over 2, which reduces to 16. All right, now let's confirm our answer using the tools of geometry. All we're just going to do is we're going to generate the graph of the function and then see if we can use the tools of geometry to find the integral. All right, so let's title this. Title it Geometric Approach. Geometric Approach. Okay, so for this one, let's go ahead and sketch what the curve looks like, the curve of the function. So we want to find out what is the integral for 1 to 5 of x plus 1 dx. We know that the geometric significance of the integral is the area between the curve of the function and the x-axis. So let's graph this. So if we have the function f of x equals x plus 1, we know that the slope is 1 over 1, and our y-intercept is 1. All right? So let's graph this function on the domain 1 to 5. So, see, goes my y-axis, there goes my x-axis. Our y-intercept is 1, so start from 1 there. And then we're going all the way to 5, right? So 1, 2, 3, 4, 5. So starting from here, you rise 1, 1, 1. Just follow that pattern all the way to 5. It's going to be at 6. All right? So this is the graph of our function. Right here is a linear function. Very easy to compute the area of simple functions like this using geometry. That's why I asked you to do it. With other functions, it's not so easy. All right, so we're going from 1 to 5. 1, 2, 3, 4, 5. So the question is, what is the area between this function that we just graphed and the x-axis? Okay, so that's what we are aiming to determine. So this region right here is the definite integral. All right, so I'm trying to figure out the area right here. Okay, so we can see that this is a trapezoid. So how do you figure out the area of a trapezoid? We know what the formula is, the area. our trapezoid is given by 1/2 uh, base 1 plus base 2 times the height. Okay? So in this situation right here, we can call this B2. This side is B2, this side right here is B1. And then this is the height of our trapezoid, H. Okay, we're just using the tools of geometry to confirm the accuracy of our results, okay? All right, so let's determine what those measures are, the values of those measures, and plug it into our area of a trapezoid formula, okay? So we can see that B1 is equal to 2. It's 2 right here, that's B1. B1 is 2. B2 is 6. You can see B2 right here, 1, 2, 3, 4, 5, 6. So B2 is 6 right here. B2 equals 6. And the height of our trapezoid is the distance from 1 to 5, which is 4 units, so it's 4. So you can see that the area of our trapezoid is equal to 1/2 times 2 plus 6 multiplied by the height of 4. All right? So this is 2 plus 6 is 8. 8 times 4 is 32. 1/2 of 32 is 16. All right, so we can see that our answer is in fact correct. So by geometry, we can see that the integral from 1 to 5 of x plus 1 dx is equal to 16 units, so our answer is correct. All right? Okay, let's take a look at number 2. So for number 2, we have the limit as the norm of the partition approaches 0 of the discrete sum from k equals 1 to n of the 183 minus the absolute value of c sub k delta x sub k, where p is any partition of a negative 2 to 1. All right, so part A is to express this limit of a Riemann sum as a definite integral. All right, so let's go ahead and do that. So we're going to have the definite integral. Now the partition, the lower bound of the partition is our lower limit of integration, negative 2, and the upper bound is the upper limit of integration, 1. Now we keep the constant as a constant, minus c sub k now becomes x. Okay, c sub k becomes x, so we have 3 minus the absolute value of x, and delta x sub k becomes dx. All right, so this is the definite integral notation of this limit of a Riemann sum. All right, part B is to algebraically determine the value of this definite integral. So algebraic approach. Now we have to be really careful when finding an integral of this function because it's not a regular function. It's a piecewise defined function, right? When you're dealing with a piecewise defined function, you will want to keep track of where the sign change happens. All right, this function is 2 in 1. So where does the sign change happen? It happens when the argument of the absolute value equals 0. Okay, so the argument of the absolute value is x. So when that is equal 0, that's when the sign change happens. So when x is less than 0, this will be minus, and when x is greater than 0, that's going to be positive. Okay, so let's go ahead and do that. So we're going to split this integral into 2. Let me show you using an interval first before I write it as an integral so you don't get confused. So what's going on here is as follows. The sign change happens at 0. To the left, the function is going to be 3 minus negative x, and then to the right is going to be 3 minus x. Okay, because we know that absolute value means plus or minus. So to the left of 0, the absolute value quantity is going to have a negative sign, and then to the right is going to be positive. All right, so we're integrating from negative 2 to 0. It's going to be negative here, and then from 0 to 1, we'll be dealing with this function right here. Okay, so before we integrate, using our formulas, we'll have the integral from negative 2 to 1 of 3 minus the absolute value of x dx becomes the integral from -2 to where the sign change happens, which is 0. In that area, this absolute value quantity has a negative sign, so this changes to 3 plus x dx. And then we're going to now go from 0 to the upper limit of integration, which is 1. And in this area, the function, this absolute value piece will have a positive sign, so it remains 3 minus x dx. Okay, so this integral right here is actually 2 in 1 because of the absolute value component. All right, so that's it. Now let's go ahead and use our properties of integration the integration rules to find the antiderivative of these two functions. And this one right here is simply going to be 3x. This had an x to 0, but if you have x to 0 plus 1 over 0 plus 1, it's just simply x. And then this is x to the 1, so you have x to the 1 plus 1 is going to be x to the second over 1 plus 1, that'll be 2 downstairs. This will be evaluated from -2 all the way to 0. And then on the function on the right, same procedure. If you integrate 3, it's simply going to be 3x. If you think about it, if you differentiate 3x, what happens? You just get 3, right? So if you integrate 3, you get 3x. Minus, here we have x to the first power, same story as this. It's going to be x to the 1 plus 1, which is 2, over 1 plus 1, which is 2. This will be evaluated from 0 all the way to 1. Okay? Now, this is pretty easy because when we plug in the upper limit of integration here, we simply get 0 because 3 times 0 is 0, and then 0 squared over 2 is 0. That minus what you get when you plug in the lower limit of integration. All right, so that's 3 times -2 plus -2 squared over 2. Okay, so that's that for the function to the left side of our sign change. Plus, on the right side, if you plug in the upper limit of integration, we are going to have 3 times 1, which is just 3, minus 1 squared over 2, which is just 1/2. That minus, if you plug in the lower limit of integration here, you just get 0. Okay, let's go ahead and simplify that and see what we get. So we have, this is -6 times this minus makes it +6, and then this is 4 over 2, which is 2, but this minus makes it -2 plus 3 minus 1/2. Okay, so we have 9 minus 2.5, which comes out to 6.5. Okay, so there goes the value of your integral. All right, let's confirm our answer using the tools of geometry, okay? So part C, we're going to use the geometric approach, just for confirmation to make sure that our answer is in fact correct, okay? All right, so now how do we graph this piecewise defined function? It's pretty easy. We can use reflection of our standard absolute value function, translation of that and reflection to quickly sketch the curve. All right. So we have the integral from -2 to 1 of 3 minus the absolute value of x. So what does the graph of this function look like? So you think about your parent absolute value function, the v centered at the origin. What translations or transformations are going to be happening with this function? Well, if you look at this function, you notice that with this minus right here, it's simply going to involve its reflection downwards. So it's going to get reflected downwards, and then this plus 3 means it's going to shift 3 units to the top, okay? So if you think about your standard absolute value function v, you flip it down, and then you shift it 3 units up, that will take us right here, 1, 2, 3. All right, so that's where the vertex will be, and then the other part is just your standard absolute value function. All right, so we're gonna go, it's gonna go in this direction, wherever. So 1, 1. Okay, and then the other one goes in that direction. All right, so what area are we trying to compute here? This is the graph of our function. What area are we looking for? Let's label it first. This is f of x equals 3 minus the absolute value of x. So we're looking for the area from -2 all the way to 1. Okay? You can see how this is a combination of two linear functions, right? So to do that, let's just partition our area right here. So we're going from here all the way to here. So the question is, what is the value of this area right here, this region here? If you notice, we have two trapezoids adjoining each other, okay? And we know what the formula for the area of a trapezoid is. This side length right here has a value of, this has a value of 3. 3 units high. This has a value of 2. And then this side length right here has a value of 1. Okay? So we know that the area of a trapezoid is given by 1/2 times base 1 plus base 2 times the height. Okay, we have two trapezoids here. We have trapezoid, we can call this trapezoid number 1. This is trapezoid 1. And then this one right here, we can call it trapezoid number 2. So area of T1, area of trapezoid 1 is going to be 1/2 times base 1 and base 2 are given by 1 and 3. Okay, so 1 plus 3 times, what is the height of trapezoid 1? It's 2 units long, okay, times 2. So let's go ahead and simplify that. We have 1 plus 3 is 4, 4 times 2 is 8, half of 8 is 4. Okay, all right, and then area of trapezoid 2 is 1/2. Base 1 for trapezoid 2 is 3, plus base 2 for trapezoid 2 is 2. All right, what is the height of trapezoid 2? It's 1 unit, right? So times 1. So we have 3 plus 2 is 6. So I meant to say 5. 3 plus 2 is 5. 5 times 1 is 5. 5 over 2 is 5/2. So 5 over 2 can be written as 2 1/2. All right? So the area under the curve that we just sketched, integral from -2 to 1 of 3 minus the absolute value of x dx is simply equal to area of trapezoid 1 plus area of trapezoid 2. And we can see that the final answer is 4 plus 2 1/2, which is 6 1/2. And that is exactly what our answer is. Okay, so that's that. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking up here. More clips can be found on Mathgotserved.com. And please post a comment to let me know what you think about this presentation. Thanks again for watching and have a wonderful day.